The fundamental concepts of general relativity do not stem out of the blue or out of nowhere or just came out unexpectedly. It arose from our day-to-day experiences, things that we see around, and when we get the results we cannot match, we cannot measure, or we cannot understand, we then need what is called a new theory. Welcome to Fundamental Concepts of General Relativity, and in this video we will delve into the very foundations of space-time and explore the stark differences as well as relationship between two essential frameworks, Euclidean space and Minkowski space. In our everyday experience, we are familiar with Euclidean space, so we know a three-dimensional realm where straight lines are the shortest paths and distances are measured using a positive definite metric. It is the space of our day-to-day navigation and classical geometry. But the question is that when we venture beyond our intuitive notions and enter into the realm of relativity, we encounter something which we are going to look into today's video. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the concepts of general relativity. First, we will deal with what is called space. And when we talk about space, that is important because that lays the foundations of any kind of a physics. So first of all, what we are going to look into is what is called a Euclidean space and what is a Minkowski space. Now, Euclidean space and Minkowski space are basically both same mathematical frameworks which are used to represent some kind of a geometric relationships which has different kind of characteristics, applications, etc., which we are going to see. Now, in general, we are aware about Euclidean space, but it is quite a good time that we should take a quick note on that. It refers to a three-dimensional space, length, width, and height, but can be generalized to any number of dimensions, and all dimensions are spatial. This diagram shows a kind of a Euclidean space where a point in a three-dimensional Euclidean space can be located using the three coordinates. So in general, it adheres to the classical geometry where the Pythagorean and other theorem holds, and we can say that the angles in a triangle add up to 180 degrees. Euclidean spaces, most important, does not explicitly incorporate time as a dimension in its geometry. The first significant important point is that when we talk about Minkowski space later in this video, first is that there is nothing or an axis which can be exclusively or explicitly determined in time in terms of time as a coordinate. It is not given, and this is what is the metric looks like. So what you do is that I will use the same Pythagoras' theorem, but I have used this for three dimensions, so x, y, and z, and I have measured the differential distance, so that is why it is ds squared equal to dx squared plus dy squared plus dz squared. So one important thing you notice is that the metric that we use in Euclidean space has a positive definite signature. Now, what do we mean by positive definite and what is not a positive definite? I will be coming into the next part of the video. But first, let us look that if we plot this kind of a three-dimensional metric on a matrix, how does it look like? And it looks exactly like this. So if you're wondering what is G mu nu, this mu nu is basically the coordinates which measures the space and time. You can look into my other videos on Einstein's field equations where I spoke a lot about this mu nu. G is a kind of a metric, but typically I have denoted a metric tensor, but here you can just denote that is any kind of a metric, say it be a Euclidean space. And this is how the matrix look like. Now, another thing which is very important to note is that the metric in Euclidean space is essentially nothing but a Euclidean distance formula which measures the distance between 2 points. Let us see what is an example. So if we take the Cartesian coordinate x, y, and z, and the distance between 2 points are x1, y1, z1, and x2, y2, and z2, then in case of a Euclidean space it would be what? x2 minus x1, y2, and z2 minus z1. All of them will be squared. Now, this is what I was trying to explain, that the term positive definite refers to what? The sign of the coefficients in the metric. So in the Euclidean metric, we say all the coefficients, once it is squared, obviously in the distance formula, they will become positive. Now, there will be a difference in terms of Minkowski space, which I will come later. So if I take x2 minus x1, y2 minus y1, z2 minus z1, so each of these terms involve the square of the differences between the coordinates of the 2 points in each dimension. And squaring obviously yields a non-negative result. Therefore, each term in the Euclidean distance formula is positive or 0, and the sum of these positive or 0 terms is a non-negative value, I mean to say the overall the distance. So this is a kind of a quick brush up which we already know, but it is a good point always to talk about what is an Euclidean space. We come next to what is called the Minkowski space, coming up in the next part of the video. Now you see, whenever I move from the Euclidean space to Minkowski space, the first difference I would say, or there are also relationship, is that it actually makes things together. It combines. What it combines? It combines three-dimensional Euclidean space and time into a four-dimensional manifold. Now don't worry about this technical term manifold. What does it mean? I have spoken about manifold in differential geometry playlist, but let us consider for the time being that manifold is just a surface. Although mathematically speaking, all manifolds are not surfaces, there are certain criteria. We will look into that later. So what happens is that from the Euclidean space, because we have got limitations and we are moving into a different kind of a relativistic world, we need a surface which will incorporate time and make into not three-dimensional space and one-dimensional time, but one single manifold, a lump of a surface which will incorporate both space and time. Now here comes Hermann Minkowski, who was a German mathematician and professor at Königsberg, Zurich and Göttingen. Now he created and developed the problem geometry of numbers and made several mathematical contributions. It is worth noting that in 1908 Minkowski realized, who was the professor of Albert Einstein, that the special theory of relativity introduced by his former student Einstein in 1905 and based on the previous works of Lorentz and Poincaré could best be understood in a need for a four-dimensional space. Hence, it is known as Minkowski spacetime, in which time and space are not separate entities but intermingled in a four-dimensional spacetime, and in which the Lorentz geometry of special relativity can be effectively represented using what is called the invariant interval. What is that invariant interval? We will soon see that. So it combines three spatial and one time and dimension into a four-dimensional spacetime continuum. So the Minkowski spacetime is a kind of a four-dimensional coordinate system in which the axes are given by x, y, z and ct. So you understand length, breadth and height, and that is time, but why it is ct I will just come up later. So this can also be written in conventional terms like x1, x2, x3 and x4, where x4 is the time coordinate. In Minkowski spacetime we call it as ct. Now you see, this ct is basically units of speed of light times the time coordinate. So c being the speed of light and t being the time, so it is multiplied together. And this can also be represented in terms of x4. But why we are not doing? Because the unit of time should be same as the unit for space. The reason is that when we are measuring time, and we see that with Michelson-Morley's experiment, that time, I mean to say, when the speed of light is uniform for all observers, obviously it has to be coupled with time. Otherwise, how will the special relativity theory stand? So Minkowski space is basically used in the context of special relativity because space-time is considered as a four-dimensional continuum. It is not a three-dimensional separate space like Euclidean space. So it incorporates time dimension along with three spatial dimensions, and this geometry is highly non-Euclidean. We will come why we are using this into the later part of the video. But first of all, let us look into a little bit mathematical understanding of how this metric would look like. So here it is, I have mentioned delta s squared, which is definitely a finite amount of chain, equals to minus c delta t squared plus delta x plus delta y squared plus delta z squared. All of these means what? Delta x is basically a perceptible finite difference, x2 minus x1, y2 minus y1 and z2 minus z1. But because we deal with infinitesimal small distances in terms of using differential calculus on a manifold, so we have to get this equation. All these are the same except that they're replaced by the differential distance d. Now here you see this g mu nu, which was a three-dimensional Euclidean space. Now it looks something like this. So we got a 4 by 4, right? So, and the matrix has got a one negative minus 1 here and another minus c over here. Now here is the point. If you really want to know that why we use minus c and why we don't use plus c, or my question would be rather, can we use a plus c also in determining the Minkowski matrix, I would recommend you to go to this lecture, which is a live lecture, Tensor Calculus live lecture 2, which is there in my playlist in the live section. I have actually given a detailed derivation on why this minus c, what will happen if this is a plus c, and what are the consequences, etc. So because this is a different kind of a video, I would request go ahead and look into it. This will give you an understanding that why it is minus c. But one thing is quite evident from this part of the video right now, that there is a minus c over here, and there is a minus 1 also in the four-dimensional Euclidean I would say Minkowski space, which was not there in the Euclidean space. So we already are getting a hint in terms of understanding. So if I take this same thing, so what we see is that Minkowski metric has a mixed signature. And what is that? It has got a negative coefficient for the time dimension and reflecting the space-time curvature of special relativity. So here is something, distance can be positive, but remember in Euclidean space what we had, the distance etc. all were positive, isn't it? So distance here can be positive, which is called a space-like. Distance can be 0, which is called light-like, or negative, which is called time-like. Now hold on, I will just explain in a few words what do I mean by space-like, light-like and time-like. In simple words, we can say that space-like means they represent distances between events separated only by spatial differences. That means there is no time, right? And you can imagine 2 points which are just separated by distance. That is called space-like. What is light-like? They represent events where only light could travel between them. I mean to say, defines the maximum speed limit according to special relativity. And you cannot really exceed the speed of light. And that was actually hypothesized with tachyons, which are considered as a hypothetical particle which might travel more than the speed of light. But anyway, that is a different part of the story that remains within the pages of the theoretical physicist. And what is time-like? Time-like involves that where the separation involves both space and time. That means whatever we are seeing in a daily world, that is the distance, etc. These are normal paths we experience, which includes both space and time. So that means Minkowski metric can be negative, can be positive, and can be 0. If it is positive, that means the distances are spatial. If it is 0, that means it is light-like. That means you have to travel almost to the speed of light. And if it is negative, that means it will include the time or the distance, whatever we are seeing. Now this is all English language, but let me quickly give you a very easy explanation through mathematics. Now here you see, if I take one event x1, z1 and t1, and I take another event x2, y2, z2 and t2, and they are whatever way they are separated. I take the same delta s squared because I am considering this to be a finite distance. I am not taking differential distance right now. And here is the xy coordinate, and x2, y2, z2 is over here, and xy, 1, 1 and z1 is over here. That is the Euclidean part. Now what I do, I replace this delta s squared with what is called r squared. There is a reason behind that. It will soon come clear. So square of the separation between the points, what we get, we take the entire delta s square, and this minus c delta t squared, because it is replaced by r squared. So x squared, y squared plus z squared become r squared, and minus c squared delta t squared. I have opened the brackets, so it remains the same. This is the space-time interval. So here is t1 and t2, and here is the distance. So c delta t means distance light travels, and delta s squared means comparing the distance light travels between the occurrence of the events. So it is quite simple. What I have done is that I have taken delta s squared to be the simple, and I have replace the x, y and z, that is the 3 spatial coordinates, by r squared, and I've just shown that t1 to t2 the distance travels c delta t, and delta s squared is nothing but the comparing the distance light travels between the occurring events. Now from where, what do we come? We come across here. So if delta s squared is less than 0, that means r squared should be less than c squared delta squared. We call it as time-like. And if delta s squared is 0, then obviously r squared will be equal to c squared delta s squared. We called it as light-like. If you recall my just a few seconds earlier, if you can scroll back to the video, you will see I have talked about time-like, which is general light-like speed, and the next thing is this one, which called delta s squared is greater than 0. That means r squared has to be greater than c squared delta r squared, and it is called space-like. So space-like means which is got a distance of space, time-like which includes both, and light-like is something where it will be equal to, and this is called null geodesics. So if you are fast enough, then you can be at event A and at event B, both at simultaneous. That is called time-like. If the two events are too far, you cannot see both of them together. That means space-like. And two events are so far that you are as fast as the speed of light. That means called light-like or null geodesic. And that is why we tell that time-like interval are for matters that has mass and travels slower than the speed of light, like human beings we are. Space-like, as I told you, for matters travels faster than the speed of light, hypothetical particles, tachyons. And null geodesics are for matter without mass, such as photons. Although technically photons do have a relativistic mass, but anyway, just for understanding, which travels at the speed of light. So ds squared, dx squared plus dy squared, this formula, if I take minus dt squared, then ds squared is -1, 0 and 1. -1 time-like, 0 is null-like, and 1 is space-like. And that is why we say that light travels on a null geodesic. So now the question is that we have understood what the Minkowski space actually deals about, what is the relation between time-like, null space and all those things. And we have saw the distinctive difference, that how it incorporates time and makes a four-dimensional manifold, and how -c comes over there. Now the question is that we all know, as you have seen in the thumbnail also, that there is something like a light cone, which obviously is a predominant factor in explaining Minkowski's space or special theory of relativity. The question is that does that light cone just arise out of anything? I mean to say, just Minkowski or Einstein thought that, okay, let us draw a light cone. It is certainly not. I would like to show you a very simple demonstration which will make things clear how this actually happened. Now imagine this person is eating or whatever it is doing, and we consider in physics this to be an event. So if I consider this to be an event, if I just ask you plainly, forget mathematics, forget light cone, that what was the past? Right now the person is eating, what was the past? And at this point, if denotes the event, you will obviously say this part, the lower part, will be obviously the past. And if these geodesics are traveling in a kind of a curved space or whatever, through acceleration, etc., somehow the figure would look like this. So we have got a past, which is something, these arrows coming right below. And we have got an event now, which is the present, which is the person eating. And if I say, okay, tell me what would be the future, what will you show? You will show this, that is, which is going to be the next. Now this actually, this structure, this I would say theoretical imagination on structure was already done many years back by this person called Lobachevsky, which is called Lobachevsky geometry, and that is a hyperbolic geometry, which was named after Lobachevsky geometry, and that was actually discovered much earlier. Now you see that this event where the person is eating, if I just get an intuitive idea of what is the past and what is the future, I cannot define this in a flat space. Obviously, we cannot. So what happens is that this hyperboloid model or the hyperbolic geometry, which was invented around 1880, if I am not wrong, by Lobachevsky, and it was renamed by various other geometers, was used into Einstein's special theory of relativity because it perfectly matches with what Minkowski spacetime predicts, that there should be a past, there should be a present, and there should be a future. Now this past, present and future was not there in Euclidean space, but because everything was at present and there was a past, if we could do the Lagrangian and calculate the particles past. So that means what? That a modern use of hyperbolic geometry is what is called the special theory of relativity. So it doesn't just came out of that. It is a kind of an understanding that the event now, what will be the past, if you draw it, we found that it cannot be defined in a space-time, flat space-time. And this hyperbolic geometry was invented long back, and pure mathematicians were working something else on hyperbolic geometry. Essentially, it turned out this hyperbolic model actually fits very well with Minkowski space. So a light cone of a particular event actually consists of all points that can be reached from that beam of light. Let us see this beautiful structure. So here you see, as I have already told, I'm just repeating with a few diagrams. These events, time-like, they can be influenced by or influenced by the observer. So it lies somewhere like this. The second is space-like. This means that they cannot influence or be influenced by the observers. Why? Because these are events that lie outside the light cone of the observer, around this part. And what is the light-like? These are events that lie on the boundary of the light cone. of an observer. This means that they are simultaneous with the observer, but they cannot be influenced. It is like somewhere like this. So now you see, in order to mention or do the mathematics of this kind of a structure, what we need is that hyperbolic geometry. So this part includes all events that could be potentially be influenced by the starting event in the future, can propagate within this cone or below the speed of light. And this part encompasses all events that should have influenced the starting event in the past. So events outside this cone cannot affect the starting event. Now, in order to summarize what we understood this hyperboloid model and Minkowski space, let me give you some certain salient points. First is that special relativity places space and time on equal footing. So what happens is that the geometry is unified one, considering space and instead of considering space and time separately. Point number 2, Minkowski space replaces what is called the Galilean geometry or the Euclidean geometry because it is a three-dimensional space. Fourth point, hyperbolic geometry enters special relativity through rapidity. That means which stands in for velocity, and we will see later that it includes what is called a hyperbolic angle. And the study of the velocity geometry becomes very important in kinematic geometry. And the fourth point is that the hyperboloid model is a way to represent the geometry of Minkowski spacetime. As I was telling you, that this doesn't come out of the blue. So it involves embedding Minkowski spacetime into a higher dimensional Euclidean space, which can be 5, 6 or so on. So the surface of the hyperboloid actually corresponds to the different events which are told in the Minkowski spacetime. Now the question is that this, I would say linking of the hyperboloid model and the light cone, what is that? Let us quickly look with some very simple definitions. First is that hyperbolic geometry is definitely a non-Euclidean geometry. That means you get something called a saddle shape, which I have shown you right on the screen. Lines can curve in unexpected ways because it's a saddle shape. Second thing is that if you see this picture, from hyperboloid we move into light cone. It allows for visualizing certain aspects of space-time curvature more easily. So the key link between the hyperbolic model and the light cones, we can say, is the fact that future light cone of an event in Minkowski space correspond to the specific hyperbola in the hyperbolic model. So whatever the light cones that you specify in future, they are nothing but they will correspond to certain hyperbola in the hyperbolic model. Also, you see, this is a very, very, very easy model in order to represent Minkowski space-time. You take any other geometry, this kind of a easy understanding won't be possible. And also it preserves the causal structure of space-time. What does that mean? That the light cones remains well defined. Now this is actually the interlinking between the hyperbolic model and the light cone. Now we will come to the last part of the video where I will like to summarize and show you that exactly what is the difference between Euclidean space and Minkowski space. Here you see another important part, that this hyperbola represents all possible paths that signals can take. That means any path, this, it can take up anything. Also, the properties of the hyperbola, such as its curvature, etc., can be used. Why? Because for the causal relationship between events in space-time. Say for example, if two events lie on the same hyperbola, they are causally connected or they can influence, etc. So the mathematics becomes very much easier. And third most important point is that the hyperbolic model provides a visual, and we are all visual learners. So we try to visualize, and geometry is all about visualization. So the model provides a visual and a geometric representation of the light cones in Minkowski space. And it offers insights into the causal structure of space-time. And obviously it poses the limitation that speed of the light, you cannot exceed more than that. So that preserves all the postulates in a nice way for special relativity. So let us look finally, wrap up in what are the differences. So Euclidean space is three-dimensional XYZ, four-dimensional XYZ and T. This happens in flat space. This happens in a hyperbolic space. Euclidean space is measured by Euclidean distance. Minkowski space is by Lorentz metric. Here its time is absolute, but their time is relative. Also, speed of light in Euclidean space is not constant. Here the speed of light is, I'm so sorry, it should be constant. I missed this one. And special relativity is not applicable. Here special relativity is definitely applicable. And the positive definite metric I showed by squaring we get the positive. But here we have got a mixed metric because it is negative. We have got a negative sign. This is ds square equals to dx plus dy square plus dz square. Here we get a minus c square dt squared. Also, the unit vectors are perpendicular. Here the time-like and space-like unit vectors, and this is invariant under rotation and translations. I'm going to say Euclidean space, and this is invariant under Lorentz transformations. So this is a kind of a quick sum up of all those mathematics and whatever I was writing to you, that what actually denotes, and this is how the Euclidean space and Minkowski space is different and what is the relation between them. So I would like to thank you very much for watching this video. Please do put up your comments in the comment section. If you have liked the video, please don't forget to click on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can also write to me at this email ID, and I would request you to subscribe to my other channel, General Relativity Explained, where I put up exclusive videos only and only on general theory of relativity. You can follow me on my Facebook, Instagram and LinkedIn pages. Thank you very much for watching this video, and Physics for Students would be soon back with more such interesting videos. But till then, goodbye.